So we're going to hear from CJ Bott.
Thank you. Howdy. Howdy. Thank you. Okay, I'm happy to be here and thank you for the invitation. I am going to discuss ongoing work with my advisor, Frank, who we all know and love. And let's get to it, last talk of the day. So first of all, Galois groups. They're something that we all know from graduate curriculum. They help us understand solvability of equations, field extensions. And yet, what a lot of people don't know is that in the first comprehensive treatise on Galois theory, Jordan also gave some examples of Galois groups in the context of enumerative geometry. We heard about this with sparse polynomial systems from Thomas's talk yesterday. I will give a quick review of lines on a cubic surface, which he also mentioned, and then I will jump into the context that I'm interested about and which my software deals with, which are Schubert problems. So we'll be talking about Galois groups in the context of Schubert calculus. So first of all, lines on a cubic surface. We've been seeing a lot of these today. Just in case anybody wasn't around, I'll go ahead and pass another one of these around. It's tradition at Texas A&M to do so. And the classic question is how many lines are on a non-singular cubic surface, one of these beautiful shapes. And we all love the answer. It's the Cayley-Salmon theorem from 1849, 27. And the beautiful thing is it doesn't matter which non-singular cubic surface you choose, right? They all have 27 lines. But there's another question in addition to this beautiful enumerative answer, which are, what are the symmetries of these 27 lines? That's the question I'm interested in today. But let's start with a more elementary example just to understand what I'm even asking about symmetries. Symmetries of the triangle. We all know triangles, right? So if you label the vertices 1, 2, and 3, using reflections and rotations, you can get all 6 different permutations of those vertices, right? However, if we go just one step further to the square, and we again label the vertices here A, B, C, and D, we cannot get all 24 permutations of the vertices using rotations and reflections. And in fact, there's a geometric obstruction to this. If you look at diagonal corners, they always stay diagonal to each other under reflections and rotations. And that geometric obstruction causes the symmetry group to be the dihedral group of order 8 rather than the full symmetric group S4. So back to lines on the cubic surface. So here, this is the picture Thomas had up yesterday of an incidence variety. We look at pairs of lines in the Grassmannian and cubics, which are given by 20 coefficients, so P19. And so we're looking at pairs where the lines are on that cubic surface, and we have a projection down to our parameter space of cubics. So if you look at a specific cubic in our base, its fiber is going to be its specific 27 lines, right? And you can do this for each point, and over this open, dense, simply connected subset, or path-connected, excuse me, subset of non-singular cubics in our base, we have a nice degree 27 covering map. Yes, thank you. And so we have a corresponding monodromy group. So just to remind you about what monodromy is, again, a cubic surface is a degree 4 polynomial in 4 variable, degree 3, get a little nervous up here, right? Polynomial, so you have 20 coefficients, and as you vary your coefficients in a loop, for each step along your path, right, you get another cubic surface slightly different from the one that you started with, and it has a different set of 27 lines. So you can imagine these 27 lines on your cubic surface moving around as you vary your parameters in a loop. But eventually you get back to where you started. You get the original cubic surface, but if you had labeled the 27 lines, just like we did with the triangle and the square, then you would notice that the labeling had permuted when you get back, or at least it possibly could have permuted when you get back to where you started. So these are the geometric transformations that we are considering, these monodromies. And the question is, which possible permutations arise? Can you get all 27 factorial of them, or is there some subset? And if there's some subset, what's the geometric obstruction to doing this? So Schläfli answered this question in 1858 by describing this remarkable incidence configuration and called the symmetry group E6. So at the bottom, you can see that the symmetry group that you get actually has 58,140 elements, way less than 27 factorial permutations. So some of the geometric constraints on the lines that cause this to occur are that every line on your cubic surface intersects exactly 10 other lines. That has to be preserved. And also, every pair of disjoint lines intersect exactly 5 other lines. So you have this beautiful geometry, this incidence relationship among your lines that constrains your Galois group to not be the full symmetric group. So this is a beautiful thing. A lot of people, when we give this monodromy type description of Galois groups, might wonder, where is the Galois theory that I know from when I was in graduate school? And so just to give an explanation of that, when we have this projection from our incidence variety down to our parameter space, this is not specific to 27 lines on the cubic. This is whenever you have our nice setup for an enumerative problem with finitely many solutions. What you get, because you have this surjective map of varieties, is it induces an inclusion of function fields. And so you get an honest-to-goodness field extension. And if you take the normal closure of that, you get a Galois extension. And there is a Galois group associated to that Galois extension. And it turns out, many proofs were given in the 20th century, that this Galois group equals that monodromy group that we had before. So they're two different perspectives of the same thing in our case, everything I'll be talking about today. Another more elementary way of viewing this is you have your system that describes how you get your 27 lines. This is a polynomial system, rational coefficients, let's say. Your solutions are going to be tuples, right? And each element of your tuple is going to be in some algebraic extension of Q. And so you throw, the smallest field where these make sense into the picture, that's some nice algebraic extension of Q, and the Galois group is related to that. So there is an algebraic side of things. I just wanted to start with the geometry. So this was a really beautiful problem, 27 lines on the cubic surface. To me, then you say, well, where can we find other interesting problems like this? And again, Thomas mentioned some really cool examples in sparse polynomial systems, but Schubert calculus has also been a very fruitful area for finding these interesting Galois group problems. So let's go ahead and give an example. Oh, by the way, we're doing math today, so we're talking about Hermann Schubert, not the famous Austrian composer Franz Schubert. So don't get confused about that. He's the one who we should credit all of this to. So my beginning example of a Schubert problem, if you hear the word Schubert calculus, don't think calculus from college. Think more like linear spaces, enumerative problems where everything is linear. Okay, so no circles. The cubic surface, this is not a Schubert calculus problem, okay? So the simplest interesting example is this one, the problem of 4 lines, and it's one that we can really think about and get our hands on. So imagine, it's not that hard to imagine because we all live in 3D space, that there are 4 lines in this room, okay? And they are general lines, which means that they don't intersect each other, none of them are coplanar, okay? And the question is, how many other lines? You have your 4 fixed ones in space, your favorite ones, random ones, as long as they're general. How many other lines in space intersect all 4 of those given lines simultaneously, right? And so to solve this, we're actually going to park one of our 4 lines to the side, and we're going to focus on 3 of our lines. It's a classic result that given 3 general lines in space, there is a unique hyperboloid of one sheet that they sweep out. They actually define one of the rulings of the hyperboloid of one sheet. But this is infinitely many solutions. There are infinitely many lines that intersect 3 general ones, and they are this hyperboloid of one sheet. Now we said this is the problem of 4 lines, not the problem of 3 lines. So we bring our 4th line back into the picture. A hyperboloid is degree 2, so our 4th line will intersect it in 2 points. And you can see then that the answer is going to be 2 lines because the 2 points on the hyperboloid of one sheet, there's another ruling, and those give you the 2 lines that are your solutions to the problem. You can also see that there is a Galois group here, admittedly a very not interesting one, which is you get the full permutation group S2. You can see this point P in between our 2 solution lines, M1 and M2. You can rotate about it to get the other configuration. So again, we have lines intersecting lines. So Schubert calculus has to do with enumerative problems involving only linear spaces. And yet there's many interesting problems already when you just restrict to that. So what is a Schubert problem in general? So you fix a vector space V over any field and a number K. The Schubert problem is to determine the number of k-dimensional subspaces of your vector space that intersect some other prescribed subspaces in prescribed dimensions. So it's a little vague, right? But let's recast our problem of 4 lines in this language just to help us understand what's going on here. So first of all, I slightly lied to you. When I mentioned the problem of 4 lines, we were really in projective 3 space, not in real 3 space. It's okay. So the question should have been phrased, how many 2 planes in C4 intersect 4 fixed general 2 planes, each in a line? So that's how you would recast our problem of 4 lines into this language of what we would expect a Schubert calculus problem to be. So then I like cooking. Maybe you like cooking, at least like eating. So I like to say that a Schubert problem has 3 ingredients. So first of all, we need to formalize what we mean by our k-dimensional subspaces of our vector space. These are going to be our solutions, our solution set. This is going to come from our Grassmannian. And then we need to formalize what I mean by some fixed things that we're going to intersect. And those are going to be formalized with the notion of a flag. And then they're not just going to intersect, they're going to intersect in some prescribed way, and that's formalized in the notion of a Schubert variety. So let's go through each of these ingredients shortly, one at a time. So Grassmannians, if you haven't seen them, as a set, they really are just the space of all k-dimensional subspaces of your vector space V. Projective space is a much more familiar example. You take all the lines in some n+1 dimensional space, that is a Grassmannian. The Grassmannian of 2 planes in C4, that is where we were looking at the problem of 4 lines. And the nice thing is that in general, although it might not seem obvious from the definition, is that the Grassmannian is a smooth projective variety. So over the reals or the complex numbers, a manifold. Now, when I first learned about Grassmannians in my differential topology class, in my algebraic geometry class, they were very abstract, beautiful, but abstract. Here, I want to get my hands on them. I want to do things with them. I'm going to show you some computation at the end of my talk, right? So we can represent Grassmannians with matrices. So for example, back to our problems of 4 lines, right? We're looking at the Grassmannian of 2 planes in 4 space. What is a 2-plane? Well, I can choose a basis for it, right? So I can instead represent it as a 4×2 matrix. And the column span recovers the 2-plane that I'm interested in. Now, this is a non-unique way to represent an element of the Grassmannian. Just like projective space, where we have homogeneous coordinates, they're not unique, right? You can imagine that. Here we have, again, a non-unique representation of elements of Grassmannians. But like projective space, where we could always set one coordinate to 1, right? For the Grassmannian, we can change our basis to have one of our 2×2 minors be the identity matrix. So here I have the first 2 rows being an identity matrix. These are some local coordinates. This is one of the manifold charts for the Grassmannian of 2 planes in 4 space. And here you can easily identify that that Grassmannian has is 4-dimensional. So you can get your hands on the Grassmannian a little better, representing it as matrices. Ingredient 2, so we have what our solutions should look like. Now we need to talk about some fixed linear spaces that we want to intersect our solutions with. That's in the notion of a flag. So a complete flag is a saturated chain of subspaces, one for each dimension up to the dimension of your ambient space. And here is a cartoon that inspired the name. You have a point, that's the top little ball at the top of the flag, and then you have the line that is going through it, and then you have the plane creating the actual flag there. So this always helps me remember what a flag is. Hopefully it does for you too. It's not exactly what a flag really looks like, but it gives you the right idea. And again, just like the Grassmannian, we can represent flags with matrices. Here we're actually dealing with invertible matrices though. So again, back to our problem of lines in space, or in other words, the Grassmannian of 2 planes in C4. We can just have a 4×4 invertible matrix, and each piece of your flag is given by, so the first piece of your flag is the span of the first column, the 2-dimensional space is the span of the first 2 columns, then the 3 columns, and so forth. So flags can be represented in this way. And at the bottom, you can see I'll be denoting the set of all flags in Cn by FLN, the complete flag variety. Okay, so the great thing about flags, this is what a flag really looks like, by the way, not that cartoon. You have a point, and you have a line that goes through that point, and then a plane that contains the line. And so once you're given a flag, fix a flag once and for all. The beautiful thing that it does for you is it partitions your Grassmannian into what are called Schubert cells. Okay, so if you look at the top, what we're doing is, again, we're going to the projective version so we can draw pictures, but let's start with a fixed flag like this and ask, how do the lines in space interact with this flag? So what is its attitude with respect to this flag? So the lines are mu that we're looking at. The blue flag is the fixed thing. And in general, what it's going to do is it's going to intersect our plane, but nothing more than that. It's not going to intersect our line. It's not going to be contained in our plane. It's not going to intersect the point, right? You have the general picture up top. One step below, if you look, you see there are some specialization that can happen. That line can intersect the line in our flag. So this is exactly the cell that we were looking at for the problem of 4 lines. So let's say you have one of our fixed lines, right, in space. You can complete it to a flag. Choose any plane that contains it, and then we're looking at all the lines that intersect that line, right? And so this picture, second from the top, kind of describes that phenomena. Or we could specialize further. And so in 2 different directions. In the one case, we can actually look at lines that are contained in the plane that still pass through our fixed line. On the other hand, we could have lines that aren't contained in the plane but go through our point, not just the line, but our point. Or you could have both simultaneously, second from the bottom, where you're contained in the plane and you pass through the point. And at the very bottom, you get the most special cell of all, which is the fixed line that you started with from the get-go. So once we have a flag, it partitions our space of, it partitions our Grassmannian into these cells. And what you can do is you can take their closure, which corresponds to, you see a hidden like Bruhat order here going on, union below. So if you look at the top and you union everything down below, you get everything, and so on and so forth. Each of these unions, these closures, are called Schubert varieties. So I'm going to put the technical definition here now, but keep this picture in mind if you get confused and lost in the details. So once you have a flag in your vector space, if you further specify what's called a Schubert condition, an increasing sequence of k integers in 1 to n, you get a Schubert variety. You get one of these closed Schubert cells. And these correspond to the elements of your Grassmannian that intersect the alpha ith piece of your flag in dimension at least I. So this is what I mean. Again, we have our solutions, which are elements of our Grassmannian. We have our flag, which is our thing we're going to be intersecting against in certain ways. And our Schubert condition tells us exactly those ways. It tells us the dimensions that our solution should intersect the pieces of our flag in. So again, a Schubert problem is not just one of these, but you give a list of conditions, and what you want to do is you get a Schubert variety for each, and you intersect all of these Schubert varieties together, hopefully getting a 0-dimensional set, and then this is going to be what we call a Schubert problem. And if you specify specific flags, we call this an instance of the Schubert problem. So just again with the problem of 4 lines, right? You start with your fixed 4 lines. You complete each of them to a flag. Each of them have the same condition, 2, 4, which says it has to intersect the 2 plane in dimension 1, a line, and it intersects space in dimension 2, but it's a plane, so it has to do that. So that second condition is trivial. And so you have an intersection of 4 varieties, and that intersection has 2 elements. So that gives you the solution to the Schubert problem. So I mentioned at the beginning Galois groups. We're coming back to Galois groups now in the context of Schubert problems. So once you fix your conditions, you can look again at an incidence variety. So you look at elements of your Grassmannian, and then you look at a list of flags. And for each fixed choice of flags, it's kind of like your fixed 4 lines, you get an instance of your problem. So we have a projection down to our parameter space, which are our R flags. So again, once you fix the R flags, its fiber is going to be the specific solution to that Schubert problem. And so again, you get a branched cover. It's going to have a Galois group, and you can ask what is such Galois group. And if it's the full symmetric group, or if it's some constrained smaller group, and if it is some smaller group, what type of geometry is this sort of thing encoding? So I realize now that I went through that pretty quickly, so let me just quickly ask if there are any questions before I get to my software on this. Everybody's good? Okay.
I just want to check what's fixed. You're choosing some particular choice of flag.
Yes.
And you fix that forever.
Yes, and you actually do this several times.
Oh, okay.
Here are such flags.
Oh, the flags vary here.
The flags vary.
Yeah, the flags are very.
So you sample some choice, like it's random.
Yes, I will be choosing, yeah, and you'll see that with my code. I will come up with some random flags. And so it's like the coefficients of our cubic, right? We're varying those. Here we're varying our flags. Just like how we always had 27 lines on our cubic surface, just like we always have 2 solutions to the problem of 4 lines, no matter how we choose those 4 general lines, that number is invariant, but we want to vary our parameters to see, again, what our Galois group is. Hopefully that answered the question.
Just one other thing. As well.
Yes, yeah, please, and thank you.
I really want to know. So like, you sample your choice of reference flag,
Mm-hmm.
then at that point, and then you have your input of like lambda mu nu
Yes.
partitions, and then you're going to somehow find a way to obtain a numerical solution.
So here, everything I will be doing is actually symbolic. I am not going to be doing the homotopy methods that have been mentioned so freely throughout this conference. And so we'll be looking at things slightly more algebraically. So I guess before I go to my code, let me just mention that one of the beautiful things about Schubert calculus is it just gives you a wealth of problems to look at. Once we formalize things, obviously you can't get a hyperboloid argument for every single one, so we had to systematize things with those 3 ingredients like I mentioned before. There are literally millions of Schubert problems that you can realistically compute on a computer. And admittedly, there's software already that can compute the number of solutions. But what if you actually wanted more than just the number of solutions? What if you actually wanted to get your hands on the actual solutions because you want to investigate them further? For example, to investigate arithmetic questions, reality, or Galois groups, which will be the application I will be discussing. That's what our Macaulay2 package will provide. This is, again, an ongoing work. We're hoping to submit it soon to JSAG. So if you update your Macaulay2 right now, it won't be there, but give it just a few months, and hopefully it will be there. So let me get to my demonstration now. So this is Macaulay2, which is for those of you who don't know, a computer algebra system. It's heavily type-based, and so it has a lot of beautiful things that can be seen either as a quirk or as a feature. So for example, if you try to take an integer matrix and you try to invert it, if its inverse isn't all over the integers, it will get angry at you, right? It will tell you this matrix is not invertible, right? You have to be very clear about the types that you're dealing with, which also helps you to not make mistakes. So for me, I see this as a feature, but you have to get used to this sort of thing when you're working in Macaulay2. So the first thing I'll do is make sure that my path is correct. Here I'm doing this in Emacs. So up top, you'll see my code, and down below, you'll see the output. So here I'm going to load my package, schubertideals.m2. And the first thing I want to do, I mentioned how both Grassmannian elements and flags can be represented with matrices. The same thing is true for Schubert varieties as well. So you can, again, just get your hands on these things very concretely. So here I'm going to be looking at the Grassmannian of 4 planes in 8 space. We're going to leave and do a new example. And I have a single Schubert condition, 1, 2, 5, 6, this increasing sequence of 4 integers. And what I get is a matrix that represents all of the elements of that Schubert variety. So here you'll notice that the 1, 2, 5, and 6 correspond to the rows, which my identity matrix will appear. But here we're not looking at a chart of the Grassmannian. Here we're looking at a locally closed subset of it, this Schubert variety. And so you'll see that my 1s have zeros above and to the right as well. So here you can read off that my Schubert variety with this condition is going to be 12-dimensional. You can also check its codimension. Oops, there we go. So this is going to be a dense open subset of the Schubert variety that we are representing here, yeah. But it's not the big cell in the whole Grassmannian, but in the Schubert variety, yes, it is. Exactly, yes, the Schubert cell. And so, yes, this is 12-dimensional for codimension. Just to make sure that works out, right? Grassmannian of 4 planes in 8 space should be 4 times 8 minus 4 dimensional, which is 16. So far, everything is so good, right? So what I want to do is I'm actually going to intersect 4 of these guys together because each has codimension 4. The whole space has dimension 16. I should expect a 0-dimensional intersection when I do this. So I'm going to generate some flags. So this is the random command in Macaulay2. You can get random flags. In our package, we'll be adjusting this slightly to allow for negative numbers. For some reason in Macaulay2, it currently only allows for positive entries. But it can do this over finite fields as well. I just wanted to show you what it looks like over Q, just to show you can do it, even though it's a lot messier. By the way, I'm only generating 3 flags here because I'm going to use the identity flag as my first flag, just the identity matrix. Okay, and so what I'm going to do now is use this method from my package called type A Schubert ideal, which is not only going to give me the number of solutions, but it's going to compute all of the equations that give me my solution. So it gives you the entire ideal of the problem from which you can extract the information that you care about. So hang on to your hats, I guess. This is a giant ideal, but it terminates. You can see the coefficients are quite large. But instantly, you can ask, what is the dimension of this ideal? It's 0-dimensional. And what is the degree of this ideal? It's degree 6. So there are 6 solutions to this Schubert problem. So already, we just generated a Schubert problem that is interesting with 6 solutions. So the next thing I'm going to do, I'm going to kind of quickly go through some other code that I've written to apply our package to the study of Galois groups. So what I'm going to do is I'm going to generate random flags over and over and over again. And each time that I do this, I get a different ideal, right? It's going to have the same number of solutions, but it's going to be a different set of solutions, right? And so, question? That's the dimension of the ideal, and that is going to be the Kroll dimension of the ideal. So if it's a 0-dimensional variety, the ideal that corresponds to it should be 0-dimensional. So that's important because if you look at the degree of a problem, if it's not 0-dimensional, you're not counting points. So that's more to just make sure.
If I put in dim I and dim comodule I, are you saying I get the same thing?
We can test it. You want to test it? Maybe after? Maybe after?
Be relevant here.
uh,
Well, it's dim R mod I.
yeah, it's the dimension of the quotient.
Comodule I do the same thing.
They found the 6 blocks.
Let's test it after. I'm afraid to do it in public, but together we can do it. And so for each instance of the problem, what I'm going to do, I'm going to do this 10 times, and then I'm going to do that 10 times. So there are going to be 100 different, what I'm going to do is I'm going to do this over a large prime. Here I'm going to do this over the prime 10,009. And I am going to get a Frobenius element, which is a field automorphism of my Galois extension that fixes my base prime field. And this Frobenius element has a cycle type, and I'm just going to extract the cycle type of that element. And the strategy here is by looking at the cycle types, I'm sampling uniformly from my Galois group. I am going to try to identify what that Galois group is. And specifically here, I'm looking for 2 3 cycles and 5 cycles. If I find a 2 3 cycle and a 5 cycle, whatever they are, it generates all of S6, and I guarantee I have the Galois group and it will terminate. So that would return true, otherwise I would return false. So it's going to take just a second. It'll be kind of in real time. That's why I broke up to batches of 10. You can see various cycle types that come. Okay, our first result came up. So it did not find a 2 3 cycle. It did not find a 5 cycle. So instead, it returns to me what cycles it did find. It found, in the first example, 5 2 2 cycles, 3 3 3 cycles, and 2 2 4 cycles. And you can see below that, again, I only found 2 2 cycles, 2 4 cycles, and 3 3 cycles. The example after that, we found the identity ones. So that's its own conjugacy class, right? Its own cycle type. But these are the only cycle types that I'm getting. If I had all of S6 as my Galois group, I should be expected to find all sorts of cycle types, right? So already I'm not finding any 5 cycles. I'm not finding any 2 3 cycles. I'm only finding these constrained ones. This will continue on, but what I'll just briefly show you is that transitive subgroups of S6 are well understood. Here's a table of all of them. There are 16 transitive subgroups of S6, and here are their cycle types and how many elements they have of each cycle type. So if I look just at 2 2 cycles, 2 4 cycles, and 3 3 cycles, there's actually only one group that has exclusively those, and that's a copy of S4 living inside of S6. I should mention that this is a toy example. It's one that's been understood for a lot of time, but this is an interesting Galois group that wasn't the full symmetric group, and we were able to identify that with our package. So I should just, before I close, mention that this package is not specifically only for Grassmannians. This works for full flag manifolds, partial flag manifolds. This works in different types. So specifically, we have things worked out for types A and C. Hope to get type B working soon. But any Schubert problem in any of those settings, the partial flag varieties of those types, they have their own analog of Schubert varieties and Schubert problems. You can get the ideal of that system using our package. So thank you all very much.
Are there any questions for CJ?
Thanks for the talk. My question is, suppose I have some random variety in the Grassmannian that I can describe for you with equations in some way. It seems to me that you could adapt your code to be able to compute its decomposition in the cohomology ring.
Yes,
right? Because you
absolutely.
just intersect it with
Really,
that.
all you need is the Stiefel coordinates for that variety, and yes, it would work.
It's an awesome talk. Thanks, CJ.
Oh, thank you.
Do you have any guess about sort of which subgroups of the full symmetric group up here has Galois groups?
Yeah, that's a great question. Yeah, and so Thomas alluded to some of this with wreath products and iterated wreath products. So Frank has a paper just for the Grassmannian of 4 planes and 8 space. Already there's so many interesting Schubert problems just in that one, and another for the Grassmannian of 4 planes and 9 space. And in those settings, he was only able to find wreath products, iterated wreath products. And so there is a conjecture that that's all that you will get. And
There's a more precise conjecture that in the paper Thomas who wrote on Galois groups and iterative problems and applications.
yeah, I should mention that for anybody interested, there is this great survey paper. Yeah, Galois groups of enumerative problems, something like that. Galois groups in enumerative geometry and applications. And it surveys Schubert calculus, it surveys sparse polynomial systems, and more. So, yeah.
I have a question. Did you ever look at the Grassmannian GR36 and the 9 3-planes?
So in 3.6, all of the problems there are well understood.
They're all full symmetric.
They're all full symmetric, in fact.
And that's a conjecture, GR3N. Okay. Should be full symmetric. It's known that they're all two transitive. Yep. There's 14 that are not just full symmetric. I mean, there's 14 that are not at least the alternating group. And we understand that completely.
How do you know they're not full?
Well, okay, on GR48, there's only about 3,500 Schubert problems that can't be reduced to a smaller Grassmannian. And there's an algorithm of Rabi-Vakil which will tell you sometimes that the Galois group contains the alternating group. We also know for many of them that it's actually a full symmetric group. Left over are 14 problems, and they've been understood completely, and this is one of them. In fact, Rabi-Vakil explained, well, Mark Derrickson understood this problem that CJ pointed out, and Rabi-Vakil generalized this to all larger Grassmannians. So a well-understood class that understands problems, and there's some other well-understood classes, but not all.
Just observationally, so apart from this, the degree of the problem, do you notice that, is there any change in like the speed of the computation depending on what the actual Galois group turns out to be? Like, is it slower when the Galois group is smaller, or I guess if it's SN, you'd expect to like right away find a transposition.
If it's full symmetric, we hope it would be significantly faster. You don't have to check everything. You'll find these specific cycle types. I showed you for S6, but there are similar characterizations for all SN. There's a pattern for 7 and higher, and then for the lower ones, you have to look for more specific things. But I haven't noticed any.
Well, computer Grover basis, it doesn't detect anything about the Galois group. It just notices how many variables and the degrees. That seems, I mean, you can make a model that fits the data.
Yeah, and as far as variables go, you know, the dimension of your Schubert varieties matters because then you have more variables. So that, you know, usually the ones with the more solutions also are like the codimension one thing over and over and over again. And that takes longer for 2 different reasons, yeah.
Well, I mean, for these elements, usually up to degree 200,
Yeah.
300, 400, and 12 to 20 variables.
Yeah. There's a, sorry.
So in your
demo here, you're only finding certain of the orbits. How do you have a termination condition? How do you know that if you didn't take more samples, you might eventually find? So
our strategy with this, because yes, this was obviously, we always do more than 10, right? I mean, we're doing thousands. My current project is to investigate this for partial flag varieties of type A. We're also playing around with the Lagrangian Grassmannian and have found some interesting things there. And there's kind of two phases. One where we, do this, depending on the degree of the problem, say like 24 times the degree, or like 1,000 or 10,000 times. And if it doesn't come out as the symmetric group that time, we kind of put it into a separate place to investigate further and run even more times just to be sure. And for all of these situations, we're just generating data. And so this isn't a proof, for example, that this is S4. This is evidence that it's S4. So there still is geometric intuition that will come into play to give the actual proof that this is what we expect it to be. But yes, you have to run this many times just to even get to the point where we want to prove something, have to really be sure.
Yeah, well, this gives a lower bound of what the proof would be, and then you have to do some math to get the upper bound, maybe.
This is the practical question, right?
No. Because it's not S6.
Okay.
Yeah, when we get symmetric group, it is a proof that that's full symmetric. It's when it's not that.
All right, let's thank the speaker again.
Thank you.